The morning of March 4th, 1944, 8th Air Force Headquarters, High Wycombe, England. Lieutenant Colonel Cass Hough stood in front of a conference table, covered with crumpled paper samples, watching senior officers pick them apart with unconcealed skepticism. These weren't battle plans or intelligence reports, they were fuel tanks. Fuel tanks made from impregnated paper. Fuel tanks that Wright Field engineers in Ohio had already declared absolutely unfeasible and unsuitable for combat operations. But Cass Hough had a problem with that assessment. His fighters had already dropped over 15,000 of them without a single failure. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The mathematics were brutal and undeniable. American B-17 Fortresses and B-24 Liberators were dying over Germany at rates that threatened to end the strategic bombing campaign before it could achieve its objectives. In October 1943, 9.1% of 8th Air Force bombers attacking their targets failed to return home. Another 45.6% came back damaged. On a single mission to Schweinfurt in August, 60 bombers out of 376 were shot down. On Black Thursday, October 14th, 77 more were lost. The bombers couldn't defend themselves. They needed fighter escorts that could go the distance. But in early 1944, no American fighter could escort bombers all the way to Berlin and back. The P-47 Thunderbolt, even with drop tanks, could barely reach the German border. The P-38 Lightning had better range, but not enough. The Luftwaffe knew where Allied escorts turned back. They waited just beyond that invisible line, and then they massacred the unprotected bombers. The solution wasn't bigger engines or better guns. It was fuel. More fuel, carried farther into enemy territory. The solution was tanks made from paper that American engineering doctrine said couldn't possibly work. The crisis that would eventually put paper fuel tanks under Mustang wings began not with engineers, but with doctrine. Before the war, American military aviation had committed itself to a theory called strategic daylight precision bombing. The concept was elegant. Heavily armed bombers flying in tight formations would saturate attacking fighters with defensive fire. The bombers would navigate by day to precisely strike industrial targets. No fighter escort would be necessary because the bombers could protect themselves. This doctrine shaped procurement, training, and tactics throughout the 1930s. It was also completely wrong. The first American bombing raid on German soil came on January 27, 1943. 90 B-17s and B-24s targeted the naval port at Wilhelmshaven. Only 58 bombers found. The target. German fighters shot down 3 bombers and damaged many more. American crews claimed 22. German fighters destroyed. German records showed 7 actual losses. The mathematics of combat attrition don't care about optimistic damage assessments. 3 bombers lost represented 5% of those reaching the target. Sustainable loss rates for bomber operations were calculated at around 2%. Anything higher meant bomber crews wouldn't survive their 25 mission tours. The losses got worse. In May 1939, Commanding General Henry Hough, Arnold had prohibited the development of drop tanks for escort fighters. His reasoning followed pre-war doctrine. Bombers didn't need escorts. Drop tanks added weight and drag. Money was better spent on more bombers. This decision, made before the war even started, would kill thousands of American airmen 4 years later, when the reality of combat destroyed the theory of self-defending bombers. By mid-1943, the crisis was undeniable. 8th Air Force bombers were being slaughtered over Germany. Without long-range fighter escort, the entire strategic bombing campaign faced cancellation. Night bombing, as the British practiced, would be the only option. Everything American air power doctrine had been built around would collapse. The United States Army Air Forces needed a fighter that could reach Berlin. They needed it desperately, and remarkably, they already had one. They just didn't know it yet. The North American P-51 Mustang had first flown in October 1940. It was designed not for the US Army Air Forces, but for Britain's Royal Air Force, which needed fighters immediately and couldn't wait for Curtiss to increase P-40 production. North American Aviation's president, Dutch Kindleberger, had made an audacious counter-proposal. Instead of building someone else's design, his company would design and build an entirely new fighter, and they would do it in 120 days. The British agreed. The original Mustang, powered by an Allison V1710 engine, was a remarkable aircraft in almost every way. Its laminar flow wing was aerodynamically revolutionary. Its radiator design, positioned under the fuselage, actually recovered some of the cooling drag as thrust through what engineers called the Meredith effect. Its internal fuel capacity, 184 gallons in wing tanks, was larger than most contemporary fighters. But the Allison engine had a critical flaw. It couldn't perform at high altitude. Above 15,000 feet, the Mustang's power dropped dramatically. This made it unsuitable for bomber escort over Europe, where combat routinely happened above 20,000 feet. The RAF used their Allison Mustangs for low-altitude reconnaissance and ground attack. They performed brilliantly in these roles. But for high-altitude bomber escort, they were inadequate. The Mustang seemed destined to remain a specialized tactical aircraft, not the war-winning strategic fighter it would become. The transformation began with an engine swap that almost didn't happen. In April 1942, the Royal Air Force's Air Fighting Development Unit at Duxford tested a radical modification. They removed the Allison engine from a Mustang and replaced it with a Rolls-Royce Merlin. The Merlin, already powering Spitfires and Hurricanes, had a two-stage supercharger that maintained power at high altitude. The combination of American airframe and British engine created something extraordinary. The Merlin Mustang could fly and fight at 35,000 feet. It was fast, it was maneuverable, and with its large internal fuel capacity, it had range that no other fighter could match. The United States Army Air Forces ordered Merlin-powered Mustangs into production in August 1942, 3 months before the first prototype even flew. The Packard Motor Company was already building Merlins under license. North American Aviation redesigned the Mustang's nose to accommodate the heavier engine, moved the wing slightly forward to maintain center of gravity, and began production of the P-51B in June 1943. But even the Merlin Mustang, with its 184 gallons of internal fuel, couldn't escort bombers to Berlin. The distance from bases in England to Berlin and back was over 1,100 miles. Even accounting for the Mustang's excellent fuel efficiency, it needed more fuel. In July 1943, as bomber losses mounted toward crisis levels, General Arnold sent a directive to North American Aviation: maximize the P-51's internal fuel capacity at the earliest possible date. Army Air Forces engineers calculated they could add an 85-gallon fuel tank in the fuselage behind the pilot. The space was available because the Mustang's radio equipment had been miniaturized, freeing up volume that could be repurposed for fuel. The modification created a new problem. An aircraft's center of gravity affects its handling characteristics. Put too much weight behind the center of gravity, and the plane becomes tail-heavy, difficult to control, potentially dangerous. A fully loaded fuselage tank shifted the P-51's center of gravity aft to the edge of acceptable limits. Pilots reported the aircraft was a handful on takeoff with the fuselage tank full, but there was a solution. Burn fuel from the fuselage tank first. By the time the Mustang reached enemy airspace, the fuselage tank would be empty. Center of gravity would return to normal. The pilot could fight without handling penalties. The modification was approved. P-51B-10 models and all subsequent Mustangs would have the 85-gallon fuselage tank as standard equipment. This brought total internal fuel to 269 gallons. Not enough. To reach Berlin and return with fuel, reserves for combat, Mustangs needed at least 400 gallons, maybe closer to 500. Internal fuel couldn't be increased further. The only solution was external drop tanks. Drop tanks weren't new. They'd existed since the 1930s. The concept was simple. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Attach auxiliary fuel tanks to external hardpoints under the wings or fuselage. Fill them with fuel. When empty, or when combat required maximum performance, jettison them. The problem wasn't the concept. The problem was production, logistics, and most critically, official resistance. General Arnold's 1939 prohibition on drop tank development had created a bureaucratic obstacle that persisted even as bombers died for lack of escort. In early 1943, when it became undeniable that fighters needed more range, the United States Army Air Force's Material Command began the official process of specifying, designing, testing, and approving drop tanks for combat use. This process, designed to ensure safety and effectiveness, moved with peacetime bureaucratic caution even as wartime urgency demanded speed. Specifications had to be written, contracts had to be bid, prototypes had to be manufactured, tests had to be conducted, modifications had to be incorporated. Then production could begin. The timeline stretched to months. The bombers couldn't wait months. They were dying now. 75-gallon drop tanks finally reached England in June 1943. They were manufactured from aluminum, pressed into two halves, and welded along a horizontal seam. They were functional. They were also heavy, requiring 60 to 70 pounds of aluminum each. They were expensive, and most critically, production couldn't scale fast enough to meet demand. Every gallon of range extension required more aluminum, more manufacturing capacity, more shipping space aboard cargo vessels already overloaded with war materiel. By late 1943, the mathematics of the bomber crisis were forcing desperate improvisations. The P-47 Thunderbolt, the primary 8th Air Force fighter before the Mustang arrived in quantity, could reach maybe 350 miles with drop tanks, barely to the German border. P-38 Lightnings had better range but were needed elsewhere. The first Merlin Mustangs, the P-51Bs, arrived in England in November 1943. Even with internal fuel of 269 gallons and 275-gallon drop tanks, they could escort to about 500 miles. This was better than anything else available. It still wasn't Berlin. The first P-51B bomber escort mission launched on December 11, 1943. The target was Emden, on the German coast, just short of Wilhelmshaven. 2 days later, Mustangs escorted bombers 480 miles to hit the naval base at Kiel. These were impressive demonstrations of range. Hermann Göring, commander of the Luftwaffe, would later reportedly say that when he saw Mustangs over Berlin, he knew the war was lost. But in December 1943, Mustangs weren't over Berlin. They couldn't get there. The fuel wasn't available. Berlin was 600 miles from England, round trip 1,100 miles, plus reserves for combat, diversions, weather. A Mustang needed at least 450 gallons total to make that mission safely. With internal fuel of 269 gallons and 275-gallon drop tanks, the aircraft carried 419 gallons. Close, but not quite enough. Larger drop tanks were needed. 110-gallon tanks would provide the necessary reserve, but manufacturing 110-gallon aluminum tanks required even more metal, more production capacity, more logistics. The United States simply couldn't produce them fast enough. This is where Hough entered the story. Lieutenant Colonel Hough was not a typical engineer. His background included civilian aviation, racing, and a near-suicidal test flight that had saved the P-38 Lightning program. In 1942, Hough had deliberately dived a Lightning at over 800 miles per hour, experiencing compressibility effects that had killed other pilots, in order to test modifications he'd developed. His courage was matched by his willingness to ignore conventional wisdom when conventional wisdom was wrong. Hough had been working on the fighter range problem since early 1943. He understood that aluminum drop tank production couldn't scale. The material was needed for aircraft structures, engines, countless other war applications. Even if aluminum was available, manufacturing time was prohibitive. Drop tanks were disposable. Single-use items dropped over enemy territory. It seemed wasteful to dedicate scarce aluminum and skilled labor to objects designed to be thrown away. Hough began exploring alternatives. What if drop tanks didn't have to be aluminum? What if they could be made from materials that were plentiful, required minimal manufacturing skill, and could be produced by facilities not already overwhelmed with war contracts. He started experimenting with paper. Not ordinary paper, impregnated paper, treated with resins that made it waterproof and structurally rigid. The technique wasn't new. It was used in civilian applications, including some aircraft components, but no one had tried making fuel tanks from it. The advantages were immediately obvious. Paper was abundant. Britain had enormous paper manufacturing capacity, including Lloyd in London, one of the largest paper companies in Europe. Paper could be formed over wooden molds by relatively unskilled workers. The resin impregnation process was simple. Production could scale rapidly without competing for aluminum or skilled metal workers, and paper tanks would be lighter than aluminum tanks of the same capacity. The disadvantages were equally obvious, at least to conventional engineers. Paper was flammable, fuel was flammable. A paper fuel tank seemed like a disaster waiting to happen. Paper was porous. How could it reliably contain gasoline without leaking? Paper was weak. Could it withstand the aerodynamic loads of high-speed flight? And paper seemed inherently unsuitable for military use. It was disposable in a pejorative sense, not robust, not engineered, not serious. Wright Field, the Army Air Force's engineering center in Ohio, evaluated Hough's paper tank proposal and rejected it. Their assessment was blunt, quote, "Paper tanks are absolutely unfeasible and will not do the job for which they are intended." End quote. The engineers at Wright Field had legitimate concerns. They were responsible for ensuring equipment wouldn't fail in combat. They understood that untested innovations could kill pilots. Their caution wasn't bureaucratic obstruction, it was professional responsibility. But Cass Hough had two advantages. First, he was in England, working directly with operational units, not in Ohio, working with test protocols. Second, he didn't ask permission. He partnered with Colonel Bob Schaefer, another officer frustrated with the slow pace of official channels, and they simply started developing paper tanks. They worked with Lloyd to refine the manufacturing process. They tested prototypes. They addressed problems as they appeared. And by late 1943, they had functional 110-gallon paper tanks ready for combat trials. The tanks were assembled from three main components: a nose cone, a body, and a tail cone. The body was formed by wrapping layers of impregnated paper around a cylindrical wooden form. Multiple layers built up thickness and strength. The resin impregnation made the paper waterproof and structurally rigid when cured. The nose and tail cones were formed over shaped molds, then attached to the body. The completed tank weighed significantly less than an equivalent aluminum tank, about 60 pounds empty versus 90 pounds for aluminum. This weight saving was crucial. Less tank weight meant more fuel weight for the same total load on the aircraft. The first operational paper tanks were attached to P-47 Thunderbolts in early 1944. Pilots were skeptical. They called them papier-mâché tanks with thinly disguised contempt. But the tanks worked. They held fuel. They didn't leak. They didn't fail under aerodynamic loads. When dropped, they separated cleanly. And when shot by enemy fighters, which happened occasionally, they didn't catastrophically explode as feared. The bullet holes leaked fuel, but self-sealing inner bladders, when used, prevented rapid fuel loss. By February 1944, 8th Air Force fighters had used over 15,000 paper drop tanks without a single structural failure. This is when Wright Field's assessment calling them unfeasible reached England. The timing was almost comically poor. The official rejection arrived after operational success had already proven the concept. Cass Hough and his team ignored the rejection. They had 15,000 successful drops as evidence. They had desperate operational need, and they had commander support from officers who understood that unconventional solutions were necessary when conventional solutions failed. Production of paper tanks scaled rapidly. Lloyd wasn't the only manufacturer. The technique was simple enough that small workshops could produce tanks. Workers didn't need specialized training in metalworking. They needed wooden forms, paper, resin, and basic hand tools. By spring 1944, Paper tank production exceeded aluminum tank production. The logistics advantage was enormous. Paper tanks required no metal. They required minimal shipping space. They could be manufactured close to where they were needed, reducing transportation burden. The first Mustangs, equipped with paper drop tanks, flew combat missions in late 1943 and early 1944. The operational difference was transformative. With two 110-gallon paper tanks, total fuel capacity reached 489 gallons. This was finally enough to reach Berlin. The first Mustang Escort mission to Berlin launched on March 4, 1944, exactly 3 years and 2 months after the Mustang's first flight. 68 P-51Bs from the 354th Fighter Group took off from Boxted Airfield in England, each carrying two 110-gallon drop tanks under their wings. The bombers they were escorting, B-17s from multiple bomb groups, were targeting industrial facilities in Berlin's outskirts. For the Luftwaffe, watching American fighters appear over the German capital for the first time, it must have seemed impossible. Captain Don Gentile, flying with the 4th Fighter Group, described the mission in his combat report. Climbed to altitude over England, burning fuel from the fuselage tanks first to restore proper center of gravity before reaching enemy airspace. About halfway across the North Sea, they switched to the drop tanks. The paper tanks fed fuel without issue, their lightweight construction causing no noticeable drag penalty compared to aluminum tanks. German fighters began appearing as the formation crossed into German airspace. The Mustang pilots kept their drop tanks attached as long as possible, maximizing range. Only when combat became imminent did they jettison the tanks. The drop sequence was critical. A Mustang with full drop tanks was heavier, less maneuverable, vulnerable in a dogfight. But drop the tanks too early, and you might not have enough fuel to return home. Pilots learned to make split-second judgments about when to drop. If enemy fighters were diving to attack, drop immediately. If they were distant, being vectored by ground control, stay with the tanks a few more minutes. Every gallon carried toward the target meant one less gallon needed from internal tanks on the return flight. Lieutenant Robert Johnson, a P-47 pilot who later transitioned to Mustangs, explained the fuel management sequence in a post-war interview preserved at the Air Force Historical Research Agency. Quote, "On takeoff, you selected the fuselage tank. You'd burn that for the first hour, maybe hour and 10 minutes, until it was half empty. This brought your center of gravity forward where it belonged. Then you'd switch to the drop tanks. You'd burn those until you saw enemy fighters, or until you reached the target area, whichever came first. The goal was to arrive over the target with just your internal wing tanks remaining. That gave you full maneuverability for combat and enough fuel to get home." End quote. The March 4th mission to Berlin encountered heavy Luftwaffe opposition. German fighters scrambled from airfields around Berlin, trying to break through the Mustang screen to reach the bombers. The Americans had advantages. Their fighters were faster at altitude. They had better visibility from the bubble canopies on later P-51D models, though the early Bs had framed canopies. Most importantly, they had enough fuel to stay and fight. Previous escort fighters had been forced to turn back, leaving bombers unprotected. Mustangs could escort all the way, fight over the target, and still return to England. The bomber losses on the March 4th mission were remarkably low. 3.5% failed to return, down from 9.1% in October 1943. Damaged aircraft rates dropped to 29.9%, down from 45.6%. The Mustang escorts had changed the fundamental mathematics of the strategic bombing campaign. Bomber crews now had reasonable chances of surviving their tours. The Luftwaffe, forced to engage American fighters in addition to bombers, began suffering unsustainable pilot losses. Hermann Göring's reported statement about seeing Mustangs over Berlin was more than defeatist rhetoric. It reflected genuine strategic despair. The Luftwaffe had built its defensive strategy around the assumption that Allied fighters lacked the range to escort bombers deep into Germany. This assumption shaped aircraft design, pilot training, airfield placement, fuel allocation, everything. When Mustangs appeared over Berlin, they invalidated that entire strategy. German fighters now had to engage American escorts before reaching the bombers. This meant air-to-air combat with aircraft that were generally superior at high altitude. The fuel that made this possible came from paper tanks that official engineering channels had declared unfeasible. Hough's willingness to bypass bureaucratic approval processes had directly contributed to strategic victory. But the story of how simple paper tanks beat complex engineering doctrine reveals principles that extended far beyond World War II aviation. The first principle is that optimal solutions aren't always sophisticated solutions. Paper drop tanks were technologically simpler than aluminum tanks. They required less manufacturing skill, less specialized equipment, less scarce materials. This simplicity was a feature, not a flaw. It enabled rapid production scaling that sophisticated manufacturing couldn't match. When the British needed tens of thousands of drop tanks immediately, paper manufacturing could respond. Aluminum couldn't. The second principle is that doctrine can become self-perpetuating even when circumstances invalidate it. General Arnold's 1939 prohibition on drop tank development made sense in a peacetime budget environment where every dollar spent on fighters was a dollar not spent on bombers. But when bombers started dying over Germany in 1943, the prohibition should have been immediately reversed. Instead, it persisted as bureaucratic inertia. Official processes moved slowly because they'd always moved slowly. Circumstances had changed, processes hadn't. The third principle is that operational necessity can drive innovation faster than formal research and development. Hough didn't wait for Wright Field to approve paper tanks. He developed them in response to immediate operational requirements, working directly with the units that would use them. This shortened the development cycle from years to months. The feedback loop between developers and users was essentially instantaneous. Problems were identified and fixed in real time. The fourth principle is that judgments about feasibility are often based on assumptions that need questioning. Wright Field engineers said paper tanks were unfeasible because paper seemed inherently unsuitable for fuel storage. This judgment assumed that materials suitable for fuel tanks must be metallic, non-porous, structurally robust in ways paper wasn't. But those assumptions ignored that paper could be modified through impregnation, that structural requirements for disposable tanks were different from permanent tanks, that flammability wasn't catastrophic if properly managed. The engineers weren't wrong to be cautious. They were wrong to assume their caution was more valid than operational testing. The statistics of paper tank production during 1944 and 1945 reveal the scale of the innovation. British manufacturers, primarily Bowater Lloyd but also numerous smaller contractors, produced over 200,000 paper drop tanks between January 1944 and May 1945. American manufacturers, initially skeptical, eventually adopted the technique and produced tens of thousands more. The total production exceeded any possibility if tanks had been restricted to aluminum construction. The weight savings were significant in aggregate. Each paper tank weighed about 30 pounds less than an aluminum equivalent. For a Mustang carrying two 110-gallon tanks, that was 60 pounds of weight reduction. 60 pounds. That could instead be fuel, ammunition, pilot survival equipment, or simply margin in the aircraft's maximum takeoff weight. Multiplied across thousands of sorties, the cumulative effect was substantial. The manufacturing labor savings were even more significant. Aluminum tanks required skilled sheet metal workers using specialized tools. These workers were needed for aircraft production, engine manufacturing, countless other applications where their skills were irreplaceable. Paper tanks required workers who could lay resin-impregnated paper over wooden forms. This was semi-skilled labor at most. It freed skilled workers for applications where skill truly mattered. The logistics savings were perhaps most important. Aluminum was imported from bauxite mines in locations like Jamaica and British Guiana, shipped across U-boat-infested Atlantic, refined in smelters, powered by increasingly scarce electricity, then fabricated into products. Paper came from trees grown domestically, processed in existing paper mills, converted to tanks in small workshops. The entire supply chain was shorter, more resilient, less vulnerable to disruption. These advantages seem obvious in retrospect. They weren't obvious in 1943 when engineers were evaluating proposals. The tendency of formal engineering to favor sophisticated solutions over simple ones is deeply rooted in professional culture. Engineers are trained to analyze, to optimize, to create designs that represent technical achievement. A fuel tank made from paper doesn't represent technical achievement in conventional terms. It represents clever use of available materials, but it's not impressive engineering in the way a precision-welded aluminum tank is impressive. This bias toward sophistication creates resistance to simple innovations, even when simple innovations are more appropriate for the specific application. Hough succeeded not because he was a better engineer than the Wright Field team, but because he understood that the engineering problem wasn't to create the best possible fuel tank in absolute terms. The problem was to create adequate fuel tanks in sufficient quantity, immediately using available resources. Paper tanks were adequate, they were sufficient, they were immediate, they used available resources. That made them optimal for the actual problem, even if they weren't optimal in abstract engineering terms. The parallel with Donald Bailey's bridge design, used extensively in the European theatre during the same period, is striking. Bailey bridges were also technologically simple, standardized panels that could be assembled by infantry using hand tools. Nothing sophisticated about the components, but the simplicity enabled deployment that sophisticated bridge designs couldn't match. Like paper drop tanks, Bailey bridges succeeded because they were good, enough, available quickly, and suitable for rapid production using non-specialized labor and materials. Both innovations shared another characteristic. They were initially resisted by official engineering channels. Bailey's design had been submitted to the British War Office in 1936 and filed away. It was only retrieved in 1941 when the crisis at Dunkirk made conventional solutions inadequate. Similarly, paper drop tanks were rejected by Wright Field even as operational units were proving their effectiveness. In both cases, innovation succeeded despite formal processes, not because of them. The human element in these stories is crucial. Hough and Donald Bailey weren't maverick outsiders. They were professionals working within military and government systems. But they shared a willingness to prioritize solving actual problems over following formal procedures when procedures became obstacles. This required courage. Bypassing official channels risked career consequences if the innovations failed. Hough's paper tanks could have caused catastrophic failures. Bailey's bridges could have collapsed under tank loads. The personal risk of advocating for unconventional solutions was substantial. Hough's background included the near-suicidal P-38 dive test. He had literally risked his life testing modifications he'd developed. This established credibility that let him push paper tanks through despite resistance. When Wright Field said they wouldn't work, Hough could point to his track record of unconventional solutions that had worked. His reputation protected him from immediate dismissal of his ideas. The organizational culture that eventually accepted paper tanks was shaped by desperation. If bomber losses had remained at sustainable levels, paper tanks might never have been adopted. The bureaucratic preference for conventional solutions would have prevailed. But by late 1943, bomber losses were threatening to end the daylight bombing campaign. This crisis created space for unconventional solutions. Commanders were willing to try anything that might work. The normal barriers to innovation lowered because the cost of failure was dropping below the cost of continuing failed conventional approaches. Captain Don Gentile, one of the top American aces in Europe, flew Mustangs with paper drop tanks on dozens of missions. After the war, he was asked about the tanks in an interview. His response was characteristically direct. Quote, "We called them paper tanks. We didn't care what they were made from. They held fuel. They didn't fail. They let us reach Berlin. That's all that mattered. If somebody had told us we could reach Berlin with tanks made from concrete, we'd have flown with concrete tanks. The mission was what mattered, not how elegant the engineering was." End quote. This pilot perspective captures the essence of why paper tanks succeeded. They solved the operational problem. Everything else was secondary. The material composition, the manufacturing technique, the engineering sophistication, none of that mattered to pilots who needed fuel to reach the target and return home. What mattered was functional adequacy. Paper tanks provided it. The Mustang's combination of capabilities, internal fuel, drop tanks, Merlin engine performance, made it the war-winning fighter for the European theatre. But that combination required every element to function. Remove the 85-gallon fuselage tank, and the Mustang's range drops below what's needed for Berlin Escort. Remove the drop tanks, and even with the fuselage tank, range is inadequate. Remove the Merlin engine, and the Allison-powered Mustang can't perform at combat altitudes. Remove the laminar flow wing and efficient radiator design, and fuel efficiency decreases enough to compromise range. The P-51's success came from integration of multiple innovations, each necessary, but none sufficient alone. This integration extended to the drop tanks. Paper tanks weren't better than aluminum tanks in most engineering metrics. They were less robust, more susceptible to damage, had higher failure rates in certain conditions like extreme cold. But they were available in quantity when needed, which made them better in the only metric that mattered. Availability beats optimality when optimality isn't available. By June 1944, when D-Day launched the invasion of Normandy, Mustangs with paper drop tanks were providing routine escort for bombing missions throughout Germany. The Luftwaffe's fighter force was being systematically destroyed. German pilots who'd trained for years were being replaced by teenagers with 50 hours of flight time. Fuel shortages meant reduced training even for those replacements. The qualitative advantage of American pilots, flying superior aircraft with ample fuel, facing exhausted German defenders, became overwhelming. The combined bomber offensive, the Joint British and American Strategic Bombing Campaign, succeeded largely because Mustangs could escort bombers to any target in Germany. This forced the Luftwaffe to engage American fighters rather than focusing on bombers. The result was a fighter war of attrition that Germany couldn't win. American production delivered new aircraft faster than losses. American training delivered new pilots faster than casualties. German production and training couldn't match this pace. The destruction of the Luftwaffe meant bomber losses dropped to sustainable levels. Missions that would have been suicidal in October 1943 became routine by spring 1944. This allowed sustained attacks on German oil production, transportation networks, and industrial facilities. These attacks degraded Germany's ability to continue fighting, contributing directly to eventual Allied victory. Paper drop tanks were one small component in this outcome, but remove them from the equation, and the timeline changes significantly. Without paper tanks, Mustang range extension relies entirely on aluminum tank production. That production couldn't scale fast enough to provide adequate numbers until months later. Those months matter. Every month the Luftwaffe survives intact is another month of bomber losses, another month of delayed oil campaign results, another month the war continues. The human cost of delays measured in months is substantial. Bomber crews dying at 9% loss rates in October 1943 versus 3% loss rates in March 1944 represented thousands of lives. If those lower loss rates had been achieved 3 months earlier, through earlier deployment of adequate drop tanks, thousands of airmen might have survived who didn't. The cost of Wright Field's initial rejection of paper tanks, measured in lives, was real even if impossible to quantify precisely. After the war, the official history of the Army Air Forces in World War II, written by the Office of Air Force History, included analysis of factors contributing to victory in the air war over Europe. The report identified long-range fighter escort as the decisive factor enabling strategic bombing success. It specifically credited the P-51 Mustang as the primary escort fighter, and, in a footnote that probably few readers noticed, it mentioned that paper drop tanks enabled the range extension necessary for Berlin escort missions. That footnote represents the difference between historical narrative and historical reality. The narrative focuses on dramatic elements: fighters, bombers, aerial combat, strategic decisions. The reality includes logistics, fuel tanks, manufacturing processes, bureaucratic obstacles. Paper drop tanks don't make exciting stories. They're not the subject of dramatic paintings or stirring memoirs, but they were necessary. Without them, the exciting stories would have had different, less favorable endings. Cass Hough received recognition for his contributions to fighter development, including work on the P-38 and on drop tank programs. After the war, he became president of Daisy Manufacturing Company, known for air rifles. His obituaries, when he died in 1973, mentioned his wartime service but focused on his business career. The paper drop tanks that helped win the air war over Europe were barely mentioned. They'd been disposable during the war, dropped over enemy territory after use. They became disposable in historical memory, too, overshadowed by more dramatic innovations. The engineering lesson from paper drop tanks extends beyond aviation. In any complex system facing resource constraints, the optimal solution is often the one that uses available resources adequately, rather than the one that uses unavailable resources optimally. Paper was available. Aluminum was constrained. Paper tanks were adequate. Therefore, paper tanks were optimal for the actual situation, not for some idealized situation where resources were unlimited. This principle applies to modern engineering challenges. When designing for resource-constrained environments, whether developing world infrastructure, disaster relief, or sustainable technology, the sophisticated solution requiring rare materials and specialized manufacturing often fails. The simple solution using local materials and basic skills succeeds because it can actually be implemented at scale. Elegance in engineering isn't about sophistication. It's about matching the solution to the actual constraints and requirements. The second lesson is about organizational decision-making under uncertainty. Wright Field engineers weren't wrong to be skeptical of paper tanks. Skepticism about untested innovations is professionally appropriate. But declaring something unfeasible based on theoretical concerns rather than empirical testing meant the organization missed an opportunity. The better approach would have been cautious, testing, limited trials, incremental adoption based on evidence. Instead, categorical rejection forced Hough to bypass official channels entirely. Organizations that create space for controlled experimentation with unconventional approaches perform better than organizations that require innovations to prove themselves theoretically before being tested empirically. The bias should be toward testing, not toward rejection. If paper tanks had failed operational trials, that failure would have been discovered quickly at low cost. Instead, they succeeded, and the main cost was the delay caused by initial rejection. The third lesson is about the relationship between doctrine and reality. Pre-war doctrine said bombers could defend themselves. Reality proved otherwise. But doctrine persisted long after reality contradicted it, because changing doctrine required admitting previous doctrine had been wrong. This organizational reluctance to update beliefs in response to contradictory evidence killed people. The faster an organization can abandon failed doctrine, the more effective it becomes. By May 1945, when Germany surrendered, American and British forces had achieved total air superiority over Europe. Luftwaffe fighters were largely destroyed or grounded for lack of fuel. German industrial production had been severely degraded by sustained bombing. The strategic bombing campaign, which had nearly failed in late 1943, had succeeded by mid-1945. This success required many factors. Long-range fighter escort was one of the most important. Paper drop tanks enabled that escort. The Mustang continued serving after World War II, seeing combat in Korea and with various air forces into the 1960s. But the paper drop tanks, being disposable, didn't survive except as museum specimens. Most were dropped over Europe, littering French, German, and Austrian countryside with cylindrical paper debris that gradually decomposed. Few were brought back to England after aborted missions and saved. These surviving examples now rest in aviation museums, most visitors walking past without understanding their significance. The Ulster Aviation Society in Northern Ireland has one such tank on display. It's weathered, the paper discoloured and brittle, the resin coating cracked. A small placard explains, "It's a World War II drop tank." Most visitors photograph the aircraft and ignore the tank. It doesn't look impressive. It's just deteriorated paper. But that deteriorated paper represents a solution to one of the war's most critical problems. It represents innovation, succeeding despite official resistance. It represents thousands of bomber crewmen who survived missions they wouldn't have survived without long-range fighter escort. Cass Hough and Bob Schaefer, the officers who developed operational paper tanks despite being told they wouldn't work, embodied a principle that military organizations struggle with. Sometimes, the correct course of action is to ignore official channels when official channels are demonstrably wrong and people are dying. This requires judgment that's difficult to define and impossible to bureaucratize. Hough and Schaefer got it right. Paper tanks worked. Their insubordination saved lives. But what if they'd been wrong? What if paper tanks had failed catastrophically in operational use, causing fighter losses? They would have been court-martialed for bypassing official approval processes. Their careers would have been destroyed. The moral of the story would have been about the dangers of circumventing proper procedures. Success vindicated their decisions retroactively. The outcomes determined whether their approach was brave or reckless. This moral ambiguity is uncomfortable for organizations that prefer clear rules. Either following procedures is correct, or bypassing procedures is correct. The actual answer depends on circumstances, judgment, and outcomes that can't be known in advance. Hough and Schaefer made judgment calls. History proved those judgments correct, but they couldn't have known with certainty at the time. They took risks, professional and personal, because the alternative was watching bomber crews die while waiting for official processes to produce solutions. The final statistics of the air war over Europe illustrate what was at stake. From August 1942 through May 1945, the 8th Air Force flew approximately 10,000 bomber missions. They lost over 4,000 bombers in combat, another 3,000 to operational causes. Approximately 47,000 American airmen died in European air operations. Another 40,000 were wounded or became prisoners of war. The loss rates varied dramatically over time. In the period before long-range escorts, from mid-1942 through late 1943, loss rates averaged between 6 and 8% of aircraft dispatched. Some missions exceeded 20% losses. After Mustangs with adequate range began providing escort in early 1944, loss rates dropped to 2 to 3%. The difference between 6% losses and 2% losses, sustained over thousands of missions, represents thousands of lives. Paper drop tanks contributed to that difference. They weren't the only factor. Better tactics, improved training, degraded Luftwaffe capabilities, all played roles. But remove paper tanks from the equation, delay long-range escort by even a few months, and the casualty numbers increase. Every bomber crew that survived because Mustangs had fuel to stay and fight owes their survival partly to decisions Cass Hough and Bob Schaefer made in late 1943. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.